take a look at the file system. So there's a file device, which is also fairly sophisticated compared to the adder or the alarm. Files work as follows. Basically, we have 8 files numbered 0 through 7, so these are like file descriptors, right, that we use internally inside the device to interact with the file. So we can load up a 3-bit file identifier. We can open a file for reading by turning on bit 6, open for read. We can open a file for writing by doing bit 7. We can open for appending by doing both at the same time. We can also delete a file by using bit 5. When we try to open a file, let's say we want to open a file for reading, we'll turn on bit 6. Bit 6 will get cleared by the device to say, okay, I've got you. And at that point, we start loading in the file name 1 character at a time. We load the first character into the data field. We turn on this bit, and it will absorb that character, clear this bit, and we can keep going. And when we're done, we load in a 0, null terminator, to the data field, turn on this bit. When it clears it, it's accepted the file name, it's opened it for reading, and as long as there's no errors, now we can do request to read to get a character. When it clears that, we can read the first character of the file from the data register, and so on and so forth. So errors, are thrown through the EOF if we encounter an error trying to open a file, or if we hit end of file when we're reading, and so on. And there's some details up here. This is also in the help section of when you say help pig inside the simulator. So we can use these to do basic file I/O. So we can work with this device through the front panel if we just want to kind of get our hands dirty. So let me take a look in the directory right now. This is our work directory, and we've got the last file created was that shortcut to the server test. So let's go ahead and open a file for writing. The file system is device 1. So let me go ahead and deposit hex into the slot register, and we'll just put in a 101. So that opens up the file device, and if I use my little dev command, I can see I've got the files process running. And then I'm going to open for write. So that's going to be a 1 in this bit 7. So that's going to be 200. So let's go ahead and deposit into CSR 200, and if I examine that register, that bit's been cleared, so it's ready to take in a file name now. So let me put in a file name. Let me put in a 101 into the data register, so that's the ASCII code for the letter A, and let me put in a 200, which again is my open for write, but in this case it means I've supplied the first character of the file name. Now I can put in a B, and now I can put in a C, and there's still nothing changed in the directory. But now if I deposit a 0 and I say write that, and I look, I've got a file called ABC, which I just created, and it's empty. And so now I can write into that file. So I can put a character in the data register and say request to write. So request to write is going to be a 20 octal. So let me put in a 110. That should be the letter H. And then let me deposit 20 octal. That's a request to write. And then let me put in 111. That should be an I, and do a request to write. And if I look at my file, it's still 0 because my outputs are buffered as usual. So I can close the file by turning on this bit 8. So that's going to be 400 octal. So I'll do that to close. And now if I look, ABC has 2 characters in it. And if I look in there, there's the H and the I that I wrote. So so pretty straightforward interface, but definitely more involved than the simpler interfaces we started with. So I won't go through that code. Let's just go ahead and use it. So there's a file called primes.mac, and does the usual boilerplate stuff in the beginning. Calls fopen with a name of a file in R0, which will open up a file for writing. It will call print byte with ASCII character 50 in there, which is a character 2, so we'll put a 2 into the file, and then I'll basically go through simple prime number generator. Each time I find a prime, I'll take a space, print that out to the file, and then I'll take our number A, and I'll call print int, which will print that number into the file. And if I have hit the last, if I flip a switch, it will exit, but it will also exit when it gets up to the largest 16-bit number it can find. At that point, it calls end program, and that calls fclose. And print int, print string, print byte, fopen, fclose. These are just built around the file device. So, for example, to print a byte, move it into the data register, turn on the request to write bit in the CSR, and then wait for that request to write to be cleared, and when it is, we're done, we've written the byte. To print a string, we just sit in a loop and repeatedly print out the bytes. To print an integer, we take our number and we just repeatedly divide by 10, look at the remainder, move that into the end of a print buffer, and then back up, take the quotient, and keep doing that until the quotient is 0. That gives us a backward scanning of the digits from right to left, and then we just call print string with the first byte in that location. So it's all just software. But we can go ahead and run this. So let's reset the bus. We'll compile that. We'll load A. And if we look at the file, the destination name is primes.txt. So let's get rid of primes.txt, and let's go ahead and run our program A, and it runs and pretty quickly exits. And if I do an ls, I've got a primes.txt, and if I look in there, it's a print out of consecutive prime numbers up to 65,000. So that's an example of the file I/O options.